The VLSM concept was born with the desire to save the company's IP addresses. If a company decides to use subnet masks /24 for all its networks, that means each subnet can host up to 254 different IP systems. 24 bits at 1 give in decimal 255, 255, 255, 0. If all of the company's subnets do host 255 physical machines, then the concept of VLSM is not necessary. But how to optimize the allocation of IP addresses if some networks have only a few machines? And how to optimize this distribution in the case of point-to-point links between routers. That is to say, links which require only 2 IP addresses. The answer is based on the implementation of the concept of variable size masks, the famous VLSM. It allows a company to divide its subnets into unequal sizes to be as close as possible to these needs. For example, in this image, the network class B 172.16.00 has been split into several subnets by applying a /24 mask to it. That is to say, in 255.255.255.0. So here, each subnet has 254 usable IPs for hosts. In this context, most host addresses are lost. Whether on user networks, or there are very few PCs, or on the links WAN, which are point-to-point links, which really only need 2 IPs. For the latter case, it's like 252 IPs lost on each WAN link. VLSM is therefore the solution to overcome this problem. It makes it possible to include different subnet masks in the same network in order to obtain a more efficient use of IP addresses. Instead of using the same subnet mask for all subnets, it is possible to use the most efficient mask for each subnet. An effective mask is one that will provide an appropriate number of host addresses for each subnet individually. For example, the subnet 172.16.10 only has 21 PCs. It doesn't need the 254 IPs that the 24-bit mask gives it. A 27-bit mask would provide 30 host addresses, which is much more appropriate for this subnet. And here is our much better, optimized topology. The subnetwork that has less than 30 hosts has been subnetted to /27, and links point-to-point now have a mask /30. In addition to providing a solution to the problem of wasted IP addresses, VLSM has another equally important benefit. It is route aggregation. This reduces the entries in the routing tables by representing only one address for all subnets. With route aggregation, the routing tables are smaller and therefore require less CPU time to do these searches. For example, the subnet 172.16.100/24 is the route aggregation that includes all of the subnets in the topology. VLSM is very important technology for large networks. It can only be used in networks that have routing protocols that support it. RIPv2, OSPF, and EIGRP routing protocols are fully compatible. Here is a very representative table because it shows the different possibilities that can be done with different subnet masks. The /24 that we see most frequently allows us to have networks of 254 hosts. 256 minus the 2 IPs not usable. That is to say, the network address and the broadcast address. Let's take another example. The start network is 172.16.0.0/20. It carries a 20-bit mask, which gives in decimal 255.255.240 0. You can see all the networks that it is possible to choose for our topology. We decide to work with the subnet 172.168.32.0/20. The usable addresses range from 172.168.32.0 to 47255. With this address and this mask, we would like to create LANs that could contain 50 hosts. For this, we will use VLSM to create subnets of at least 50 IPs. Looking for the need of at least 50 guests, we will leave on a mask in /26, which allows you to get 62 hosts per network, 64 minus 2. We will therefore borrow 6 bits from the host's part. And 6 to the power of 2 gives us 64 IP minus 2, which makes 62 IPs usable for our subnets of 50 hosts, which is much better structured than our starting mask in /20, which allowed us to make networks of more than 4,000 IP. Here is the possible breakdown of our subnet 64 IP. I recall 62 usable. We can now distribute the subnets to our equipment of 50 hosts. For the WAN links, it would be a shame to apply the same mask, because as this is a point-to-point network, only two addresses are needed. It would therefore still be a waste of address. Looking at the table of subnet masks, we can see that a /30 would be perfect for point-to-point networks, because 2 IPs are fully available. In total, there are 4, but since we cannot use the network and broadcast address, we therefore have 2, exactly what we need. And here is our topology, which has a lot less addresses to waste than with a /24. We have /26 for networks with less than 62 devices, and /30 for our point-to-point networks. When we do VLSM, we must always start with the largest subnets for splitting, identical